Hey there, my name is Ford Brett, and I'm CEO of PetroSkills. And today, for the next hour, really 45 minutes with questions, I'm going to talk about the perfect well ratio. And what the perfect well ratio is a concept that quantifies how much drilling performance is possible. So it's like, how much can we improve? Well, this tells us how much we can improve. And it compares it with perfection, which is an interesting idea. And there's some good things and bad things about this, what we're going to talk about. But I'm going to answer 4 questions, which is basically, what is this and why would it be any good? You know, how can we determine the perfect time? And perfect time would be perfect. You couldn't actually do perfect, but is what would happen if you did perfect? And how does the perfect well compare with the technical limit and say days per 10,000 feet, kind of other benchmarks? And then how can we use the perfect well to do some good? And hopefully, you'll be able to identify where to focus drilling improvement efforts to get the most bang for your buck. If there's a lot of improvement possible, maybe you can do it. If there's not very much improvement possible, maybe you're pushing on a rope, not something you should be working on. There's a references here, American Association of Drilling Engineer paper and a patent that I've listed there. And as Clay mentioned here about questions, you know, we have 150 people or so signed up for this thing. I don't know how many joining, some number like that. It's not really possible to take questions and still stay to an hour schedule if we jump off, but you'll see the page numbers down there in the bottom. If you put questions with your slide reference to slide number, that would be helpful too. But hopefully we'll get through with this and be able to answer some questions. And so let's see. We're going to talk, first thing, talk a little about safety and well construction time. Because faster is almost always cheaper. I guess you can overspend going fast. But if you reduce the time to drill a well, it's normally almost always, hate to say always, but almost always cheaper. Here's an example of days versus depth in the Gulf of Mexico, and a situation where they drilled a well and they thought it was going to take 45 days, ended up taking 90 days, 14,000 feet measured depth, about 4,000 feet of water, collected 256 improvements, and next well, hey, 264 improvements. It was better, it was faster, and so it was way deeper, much faster, very similar area, so it's not geologically way different. Okay, so let's see, but hey, cheap's good, that's good. Cheaper is better than not, but wait a minute, safe is more important than cheap. So what does faster mean for safety? We're going to talk about perfect, going faster. What's that mean? So which is faster, or which is safer, this old way or the new way? Let's look at that, which is safer? Dang, let's see. Let's look at this. Have one well drilling the old way, and we do that, and then let's have one well, one rig drill the new way. So let's see, which is safer? Well, let's see, this new way, we're going to enter 4 more reservoirs. So we got 4 more kind of dangerous situations we're doing. Let's see, maybe going too fast is bad. Hey, fast, kind of speed up, people running, stuff like that, that's maybe not be good. So maybe if you said one well, one rig doing the old way for 1 year, compare that with one rig doing the new way for 1 year, you know what? Maybe the old way is safer. Maybe in turn, depends on how much risk associated with well control and so forth. But you know what? That's not the right comparison. You have to compare 2 rigs drilling 8 wells per year compared with 1 rig drilling 8 wells per year. And most unsafe thing about working in the Gulf of Mexico is driving to the helideck. The next most unsafe thing is flying to the helideck. And basically, these 2 rigs are going to have, when the holes open longer, it becomes unsafe. And so, fast to the point of unsafety is not good. But if you're talking about getting fast to performance per number of delivery, which is wells, making things so the well's not open as long, making things so we have less people driving to the location in the middle of the night, making things so you have less handovers for things to go wrong, is not arguably more unsafe. And so don't want to throw out safety, and safety's super important, or more important than cost, that's for sure. But faster does not necessarily mean more unsafe. So we want to keep that in mind when we talk about this. And so I'm going to answer 4 questions. And the first question is, what and why define a perfect well? I'm going to do this in 90 seconds here so you kind of see the summary. And basically, the perfect well is the fastest, physics and the rock says you can break it and drill it and construct it. So it's the fastest possible time. You know, it's faster than the technical limit. It's not possible to drill the perfect well. Okay. So if that's what it is, why would I want to do that? It's not possible. Why do I want to do it? Well, you understand if and how much improvement is possible based on an objective standard. And other approaches take a lot longer and are prone to bias. And so it is a way to give you an estimate of how long something can be drilled. You can compare what you're currently doing with that to say, this is improvement that is possible. And now how to get it's another question. But so how do you estimate a perfect well's time? Well, there's a spreadsheet in 15 minutes. So this is pretty easy to do. I'm going to just show it to you and have an opportunity to download a spreadsheet later on. We'll talk about that, but make your own if you want to, but we'll have one that's available. And basically this idea, you can use this without doing perfect well by kind of describing what is completely possible, and we'll compare how this is different than the technical limit in a little bit. But basically what it does is it uses the mechanical specific energy concept and a sonic travel time estimate based on rock strength and flawless operational times to construct the perfect well. And there's a patent described there you can look at that describes this process. And it takes about 10 or 15 minutes to plug these numbers into the spreadsheet to do it. And so basically, I'll show you how it's calculated and what you need to do that, but that's a quick answer to the question. Next question, how does it compare with the technical limit in days per 10,000 feet? And my answer is it's a better benchmark. The reason it's better is because it's completely quantitative. Days per 10,000 feet is quantitative, but there's some problems with that. It's fast and easy to do and quickly gets you on to discussions about what can we do to improve instead of about how much improvement is possible. Because how much improvement is possible is not really a productive conversation. What can we do to improve is very productive conversation. And so how can you use the perfect well to do some good? Well, you can use it to benchmark drilling performance from different types of wells, and I'll show examples of this from kind of completely rank exploration to routine development. Helps you identify opportunities for improvement. So, and I'll show some unconventional and development program examples of where should we spend time to try to improve. And it can help you bound well cost estimates, and I'll show you some exploration examples of that. So let's see, that was a short answer to the question. Getting into the question answers in a little bit more detail. Why define the perfect well? It's quick, easy, and quantitative. You know, it takes 10 minutes, 15 minutes. It helps you identify opportunities to improve based on a non-arguable benchmark. Because when you compare with perfect, you know it is possible. You can't do better than perfect, so what's the difference between perfect and now? It normalizes the difference between wells so that you can compare wells that aren't exactly the same, and I'll show you some examples of that. And I think the most important point of this is it changes the conversation from arguing about what the performance metric is to understanding the causes of the deviations from an objective standard. You say, this is possible, now what can we do to improve? Not, what improvement is possible. And the perfect well, by the way, is just a start. It delivers an easy way, quantitative performance benchmark, kind of gets this conversation going. What doesn't it do? It doesn't do thinking for you. It doesn't say this is how you're going to improve. I'll tell you how to improve. You don't know how to do that. It just says it can be done. And it doesn't get team members on the same page. It can help get people on the same page. But there's a way that you use it, interact with people to kind of get people in operations, with the contractors, with the clients who you're drilling the well for, to understand what's possible. But it does force healthy thinking, so we can start thinking about that. So let me see. That's what the perfect well is, and so let's look at it a little bit more detail. So think about the components of a well's duration. Well, the perfect well is the physical limits of technology. That's 1 bit per hole section. That is the penetration rates limited by the bits are perfectly sharp all the time. Perfect bottom hole cleaning. We're not waiting on cement. Perfect well wouldn't wait on cement. It's just the perfect time. The technical limit is the limits of technology. We might need more than 1 bit in a hole section. That wouldn't be perfect. You know, maybe we do need to circulate bottoms up to make sure we don't have fill on the bottom of the hole. You know, perfect mud would suspend the solids, wouldn't it? Yeah, it would. Well, you know, real mud's not perfect, so we can't, we got to circulate bottoms up before we run casing, say. And so there's, you know, a technical limit. There's operational skill-based waste. And so these are things that are like, you know, we're nippling up. Well, what's the perfect nipple up time? Well, we're not doing it as fast as is humanly possible. You know, things like we're tripping slower than is actually possible because we might be pulling up into a section that will get stuck. And so those are kinds of less than perfect performance, doing things kind of good enough, but not the technical limit. And maybe they're good to do, but they're not perfect. You know, there's waste due to decision processes. And so this is less than perfect performance due to improper design or operational plans. And so let's see, you know, we're going to set casing setting depth as conservative to be safe. And so we're going to make a decision to do that. And that kind of, we could do it better, but we're going to decide not to. So it's not the technical limit, but it is, you know, an extra casing string. Maybe it's safer. Maybe it's, you know, keeps the hole from falling in, but it wouldn't be the technical limit. You had the perfect wellbore stability, you know, mud, or drilled the whole section fast enough so it wouldn't react or something. Maybe you wouldn't have to do it. But so there can be waste due to decision processes. There's loss due to operational skill. And so this is like, oh, dang, we got stuck. We stayed in one place too long. We ran a cone off a bit. So that's operational skill lost. And there's also loss due to decision process. So for example, we set casing in the wrong place, and so that causes the hole to be unstable. That causes us to get stuck. We had a geologic sidetrack because we decided, you know, we didn't do our directional program correctly. We used the wrong mud, and so, oh, dang, we made a wrong decision, so that caused hole problems and so forth. So basically, you know, the perfect well is way, way faster than what actually happens. And I'll show you this. There's perfect well ratios. Some remote wildcat wells are 30 times perfect. I'll show you some examples of this in a second. And so most wells actually fall in this range here. This is roughly drawn to scale, by the way. I'll show you this with real wells in a second. In other words, perfect is way faster than we normally do most operations. And so why is that helpful? Well, show you why it's helpful in a little bit. So kind of, you can think about this in this loss is like non-productive time. It's things going wrong. Waste is things, so it's like drilling efficiency. It's like it's not as efficient as it could be, so it's a little bit wasteful. And so, you know, waste and loss and waste are quality management concepts, you know, from total quality management. And, you know, waste is less than total quality that's a result of process operating normally. So, for example, McDonald's throws out French fries when they get too cold, so they're wasting French fries. But they do that so that because they can only keep them so fresh for so long, and they want to have the fries available, so they throw out cold French fries, and that's waste. You know, circulating to condition mud. We got to circulate to condition the mud because we need to, you know, get ready for the next hole section. Well, that's waste because, you know what? In a perfect world, you wouldn't have to circulate to condition mud. You'd mix it and it'd be perfect. There'd go. You know, in a perfect world, well, it's not a perfect world, so we got to do stuff like that. Well, that's waste. Loss is less than total quality as a result of some kind of process failure. So I dumped a bunch of French fries on the floor. Well, that's a loss. You know, I got my pipe stuck. Well, that's a loss. And so these are two different ideas about loss and waste. And the reason that's important about this is that waste, to improve waste, you have to change something about changing the process. Loss is like a special cause that you have to prevent and make sure that you manage the process so that the process doesn't fail. But waste, you have to improve the process because the process isn't working. And so there are actually two different classes of root causes to loss and waste. You know, one of them is due to decision process. So that's, you know, it's less than perfect due to thinking incorrectly. So, you know, sometimes, give you an example, we're going to talk about golf here in a second. I'll play golf, and you play golf in Colorado, where high altitude, you I don't know what club to use. You know, how far does a 7-iron go in Denver? Well, it goes farther than here, so you can pick the wrong club. So that would be a decision process. You know, operational skill is, you know, some kind of action. So I've got the right club, but I just hit it wrong. And so I'm going to tell you an interesting thing about sports analogies. We're going to talk about golf here in a second with this. And one time I was using an example for golf, and my wife said, golf, you know, everything in the world is not like golf. And I said, yeah, honey, you're right. Those things in the world that aren't like golf are like football. Anyway, I've also heard anyone uses a sports analogy doesn't know what they're talking about. So, because they're never exactly perfect. But with this idea, you know, a human has hit a golf ball 515 yards. That has actually happened before. And by the way, since a person has done it, you know, perfect would be better than that. I haven't done analysis of this, but you know, how fast can you physically accelerate a golf ball, and how far could it go? Well, it's farther than 515 yards. And so, depending on trees or what you could do to slice it or something, you know, perfect is almost like a hole in one. There might, you know, 610-yard par 5, you might need 2 strokes, but you know, you ought to be able to get around a golf course in 20 strokes, 23 strokes, you know, 18 some of them. Well, the technical limit is like an eagle or a double eagle. You know, really, there are you can't hit a golf ball perfectly in the air and have it land in the cup. You know, so you know that's kind of the technical limit. Well, operational skill waste would be something like lagging a putt. So I'm just going to get the putt close. I'm not going to put it in. I'm 30 feet away. Well, you know, you can put it in the hole. And by the way, Tiger Woods doesn't lag putts. He's trying to sink them. Well, I think I'm going to lag a putt. Just get it up close. That's fine. That would be an example of operational skill. Waste due to decision process would be misreading a green. I think it's going to break to the right. You know what? It went straight. Well, that would be a decision that caused a problem. You know, operational skill loss, I just sliced the ball into the water. And then a decision process, I used the wrong club, and I hit it over the green into the water. Well, so those are examples of how this is. And what you need to do to improve depends upon, is it a loss or waste? And what this perfect well idea helps us do is try to understand that. And so how do we calculate the perfect well? Well, let's see. There's one part of this is what's the time to actually cut the rock? So what would be perfect for actually physically drilling? Well, there's a paper by Ernie Onya that talks about correlation between sonic travel time and unconfined rock strength. And so if you have a sonic log, you can get a pretty good estimate of the rock strength. I'll talk about that a little bit more detail about that. So how strong is the rock? And if you look at that's the unconfined rock strength. If you look at the mud weight and say we're going to be 100 psi overbalance, so we're going to be safe to be 100 ps, safe. Warren Winters has an SB paper that talks about correlation between confining pressure and rock strength. You can come up with apparent rock strength from that. So I got the unconfined rock strength from sonic log. Talk about the confining pressure that it's under. We can get the apparent rock strength. And then with the mechanical specific energy, we can say, how much area are we drilling? What's the specific energy? How much horsepower are we putting on the bottom of the hole? Well, what's the maximum penetration rate? You know, what can we physically not drill that rock any faster than? And so Pressier has an SPA paper that kind of describes this. And you can say, how many feet did I drill? And that will tell you the minimum time to drill an interval of hole. You cannot drill it faster than that. If the rock, because it depends upon the amount of energy you're putting on the hole, and assuming there's a mechanical efficiency for cutting the rock, 80%, which probably is, and the bit's perfectly sharp, that's the amount of time it's going to do that. You can't drill a hole faster than that. And so it doesn't mean you can clean the hole, but perfect would have the hole perfectly clean. And so this sonic travel time correlates reasonably with unconfined compressive strength. And there's that example there. The compressive strength is a function of unconfined compressive strength and the confining pressure, the mud weight and depth. This is the Warren Winters correlation. They do correlate. And so it's easy and fast to get a good estimate of the time to cut a rock based on the specific energy concept. Okay, so couple words about this mechanical specific energy idea. Yeah, it's an old bit penetration modeling concept, old kind of from the 50s. I think Ernest Lubinsky came up with this. And it's very useful for understanding efficiency over a particular run. So you can look at the specific energy as it changes in a bit run and kind of figure out what's going on in terms of things that are affecting how performance is happening. You can see if you're operating it properly or if it's getting dull or so forth. But it's not often predictive because there's one factor that lumps into this model for bit wear, cutting efficiency, drilling conditions, hole cleaning, and rock strength. And so you can see how things are kind of going wrong and starting to go wrong, but you can't say, I'm going to put a bit in the hole and 2,000 feet from now, what's going to be the penetration rate? Because all these other confounding factors are involved. And so it's a good concept and very useful to improve efficiency as you go through, but you can't say, what's my penetration rate going to be at 15,500 feet, 2,000 feet into a bit run, because all these other factors are taken into account or lumped into there. But interestingly, with a perfect well, I always have a sharp bit. I always have optimum efficiency. I always have perfect hole cleaning. So if you know the rock strength, you can say, what's the fastest I can possibly drill that interval of hole? You can't drill it any faster than that because you got to break rock into chips. Breaking it into chips takes energy. You put energy on the bottom of the hole. You're not going to break it any faster than this estimate. And so it correlates with rock strength. Sonic travel time does this. And so you can create a reasonable estimate of the minimum time required to drill a hole. There's references here for you, Durtonay, Precia, Rebbia, and Teal, that have different descriptions of this concept, which are useful. So that's one thing. Of course, drilling the hole is only part of what you're doing. You also have other things. You got to, with case holes, I guess we cannot not have casing because we have pore pressure and we have to, take that into account. So basically, what would perfect be? Well, let's have some estimates of flawless operation for other operations. So, we're going to drill out and do the formation integrity test. It's going to take 1 hour. We're going to do that because we need to do that for safety. We're going to cut the rock. Okay, 1 bit per hole section. So we're going to trip in in case hole at 5,400 feet an hour. We're going to trip out in open hole at 3,400 feet an hour. Wireline log at 2,000 feet in 1 pass. If we wireline log, what if we don't log? Well, then we're not going to do that. We mix and pump cement. We don't wait on cement. So these are some estimates of some perfect, really good times. Probably can't do that, but maybe could be done with physics. And so basically, a perfect well would have these times and drill the rock as fast as you possibly could. And so that would allow us to calculate it. And I'll show you the spreadsheet in a second, how that works out. And so what do you need to do to estimate this stuff? Well, for perfect benchmark wells, like wells you've already drilled, you need the pore pressure versus measured depth and true vertical depth. A hole diagram, casing points, casing sizes, hole sizes. The duration of spud to bump the plug, and a sonic log. You can also get sonic travel time from a seismic, but that's of course not as accurate or is not as certain and is more lumped than the sonic log. If you have a prospective well you're going to drill, well, what's the pore pressure you expect? Now, it's going to only be, your estimate's only going to be as accurate as that. If the pore pressure is way wrong, the estimate will be way wrong. If you have a sonic log from an offset, that would be helpful. If you don't, sonic travel times from seismic in frontier areas can tell you, estimate that. And then what's the whole program that you expect? But from those, you can calculate perfect well time. And so there's a spreadsheet that you'll be able to license, or not license, we're going to give it to you. But I want to, you can download this. You'll have an email that afterwards that will provide you a link for this. And you get, so to use this, how do I do this? I get my whole program, my sonic log pore pressure plot, and then I use this freeware to estimate the rock strength from sonic travel time and to compute the perfect well time ratio. And so basically you go in and you say, well, what's the water depth? Is it water? What's the yeah, there's going to be a link for this, by the way. We're going to give you this. You know, what's the hole size, casing setting depth, and so forth, and it'll spit out the perfect well time. And so this is a, you know, so use this freeware to do this. Now, basically, we've got, this is a patented process, and the reason I wanted to patent this is because I didn't want people just bastardizing. I say, this is what the perfect well is. This is what it is. Now, it's licensed for your professional use. You agree not to sell it, so I'm not selling it, so don't sell it. And, you know, and by the way, you're not going to sue me. You know, you can use this as long as you don't sue me. If you sue me, you can't use it. And if you have any improvement suggestions, you know, please let me know so we'll kind of get this better with time. But that's, and so we'll have it available to see this. And so we'll talk about using this in a second and how this works. And so how does this compare with, so, okay, so dang, so, okay, this is a benchmark, performance benchmark. How does this compare with the technical limit in days per 10,000 feet? Well, let's see. How does it compare with the technical limit? Well, it depends on what technical limit you're talking about. Let's see, some technical limits, and this is the original idea from Dave Bond in Australia, was the technical limit is the shortest possible time a particular well can be drilled with a particular set of equipment. So that's what the technical limit is. So how does the perfect well compare with that? Well, it's about 50% faster than that, and I'll show you what it is. And it can be easily known. Perfect well can be easily known. The technical limit, this technical limit can't be so easily known. There's another technical limit floating around, and that is the estimated well duration generated by a group of experts or experienced people who consider the best possible time to drill a particular type of well. So we'll have people sit around and say, we're going to decide that we're going to find a technical limit. So what are we going to do that? We'll get all the people to know how to drill in the area, and we're going to go through the well step by step and come up with a technical limit. We do that. Well, how does the perfect well compare with that? Well, first of all, the perfect well is unarguable. And so what is this technical limit? That's basically people do is they argue about it or discuss it. And that's not wasted time. So I'm not saying that's not a useful process or helpful. But, you know, it isn't completely unarguable. It's not always as quantifiable as this. And by the way, this takes a lot more time to calculate. One thing about a lot of technical limits, we beat the technical limit. Well, you didn't beat the technical limit. You improperly estimated the technical limit, because the technical limit is actually the shortest possible time it can be drilled. It's not what you happen to think the fastest time is. And so what the perfect well does is helps to actually find the answer to this A1 here. And so here's an example of comparing perfect well days on a series of Gulf of Mexico wells. This describes this in more detail. And so there's, 2, 4, 6, 8 deep water wells, and this was the technical limit days estimated by a half day and a half process by experts, kind of going through and defining the real technical limit. So each one of these things took many people many hours to come up with. So what's the technical limit on this well? Well, let's sit down and describe it and think about it. And we say it's 11 and a half or whatever. Well, in 15 minutes, calculate the perfect well and say, hey, the perfect well is 4.1 days for that well. Look at the correlation between these things. It takes an hour and a half to calculate the perfect well ratio on all of these different wells. It correlated with 97% correlation. And it basically said it was 1.9 times the perfect well. Take the perfect well, five days, multiply times 1.9, and then add this 3.2, which was basically the deep water riser time. The perfect well doesn't have any deep water rising time calculations in it, so we don't manage any time with this. And so basically, it was minutes versus hours and hours and hours and hours. And a lot of times, the technical limit is beaten because the people who come up with these estimates, don't actually, are a little bit conservative, I guess. I want you to remember this number, 1.9, basically. This number comes up again. Another thing, 1.9 times the technical limit. So that's one way that it compares with the technical limit. Basically, it's about 1.8 times the perfect well. Multiply the perfect well times 1.8, and you'll come up with the technical limit. So how does it compare with days per 10,000 feet? Well, days per 10,000 feet is faster to calculate than the perfect well. It takes about, how long does it take days per 10,000 feet? 20 seconds. How long does it take to do the perfect well? 15 minutes. So days per 10,000 feet is about 15 minutes faster than the perfect well, okay? But the perfect well is a way better benchmark. And here's an example of a study of 20 deepwater Gulf of Mexico wells that compared the perfect well with the days for 10,000 feet. And what I've got plotted up here is the number of hole sections and the perfect well ratio for these different wells and the days per 10,000 feet for these different wells. And so, for example, the problem with the days per 10,000 feet is it's confounded by the number of hole sections or the amount of casing strings you're running. And there's a 41% correlation between number of casing strings and days per 10,000 feet. If you're drilling a 12,000-foot well and you have, 7 casing strings, is it going to be more or less days per 10,000 feet than if you have 3 casing strings? Well, obviously it's going to be more days because you got more messing around with casing. And so, this might be a useful benchmark for 7 strings, but you can't compare 7 strings with 5 strings. So, for example, we got a well that's 60, days per 10,000 feet, 60 days, 60. So all these different times, this well right here had a perfect well ratio of 5. This well right here had a perfect well ratio of, 6.5? This well is way better than that well because we're getting all this number of casing strings done and all this work done, and we're not confounding these things. And so perfect well is uncorrelated with number of strings, so it normalizes differences. So how far are these wells from the technical limit? Well, I said, and I'll show you this in a second, technical limit is about 1.8 times the perfect well. Here's an example of a well right here with 5 casing strings that had a perfect well ratio of about 2.4. That well is very, very good because that's very close to the technical limit. Here's an example of a well that had 3 casing strings, had exactly or very similar days per 10,000 feet. Interestingly, the perfect well ratio there is 4.9. That's not bad. I've seen perfect well ratios of 35. That's not bad, but that's not great. That has the same days per 10,000 feet. And so this kind of helps unconfound these things. And so that's, a quick comparison of these two kinds of things. So let's see, last question here the last thing I'm going to cover here, question I'm going to answer before we start getting to some questions, hopefully. And that is, what can you do with this? Well, you can benchmark performance, you can identify opportunity for improvement, and bound well cost estimates. And again, the reference in an oil and gas journal article describes this in more detail. But basically, calculate the perfect well for thousands of wells worldwide in a whole bunch of different areas, and kind of average and high and low. And anyway, the low was 1.8 and the high was 30. And I've since, told you I've seen perfect well ratios of up to 37. So, and have seen 1.8, and the 1.8 perfect data point that was actually calculated was in an area with very, 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 very well-known geology. Was in an area when the rig count was normally about 15 and has gone to 1. And when there was no uncertainty in what the plan should be, so you've got the best rig, the best crew, scared you're going to lose your job, and they actually probably did drill very, very close to the technical limit. A lot of times it's not that case, though, and I'll show you what happens. So if you look at all of these different types of operations, we found the best observed perfect well ratio. The average of the program for the perfect well ratio. So some of these operations, here's a 15,000-foot wells in the United States. Well, the very, very best perfect well ratio was, 3.8. That program average there was, what does that look like, 4.5 or something like that? And then the worst one was 8. So kind of describe those. And then what was the first well in the development, or maybe the P95, so, the 5% worst well if there was more than that, and then kind of compared it with the technical limit, and then compared it with other, best-in-class kind of things. And so here's an example of a well where a process, they came up with the technical limit, and the technical limit was 4. Well, actually, in this particular case, Oxy actually drilled better than the technical limit. Well, that means that wasn't the technical limit. So they actually, beat it. Other examples where people calculate the technical limit, they kind of come in at 2. But you can look at this and you can say, rank exploration wells where you do not have very much knowledge, you don't know what's going on, you're going to have a lot of waste and loss through the operational and decision. Perfect well ratios at 12 to 16. If a difficult exploration well, maybe wells we have more information but still kind of technically difficult, faulted, that kind of stuff, maybe 7 to 12 perfect well ratio. A routine development activity, perfect well ratio of 3.5 to 6, kind of a normal activity places happen, and then or say difficult development, and then routine development where you don't have a lot of problems and have a lot of information, maybe 2.2 to 3.5 would be kind of a decent perfect well ratio. Another way to think about this is if perfect would be 100% efficiency, the technical limit is operating at like 55% efficiency. In rank exploration wells, maybe we're operating 7% efficiency. So kind of thinking about it this way, if you're thinking about motors, let's see, what's a lawnmower engine, 2-cycle gasoline engine? How efficient is that thing? Well, I don't know. How much energy are you putting in terms of gasoline? Well, we know how much energy we're putting in. How much work do you get out the shaft? Probably 17%, 15%, 20%, something like that. A good lawnmower engine might be 25% efficient. That'd be really good. What about a efficiency of a giant electric power plant, combined cycle gas turbine? How efficient are those things? 55, 50%, something like that. So, in a power plant, that's good efficiency. And so this is kind of ways to look at it. And of course, exploration wells where you don't have much information, you're going to have loss due to decision process because you don't have information. Well, this kind of helps us understand what normal is for this. And so once we kind of understand what normal is, we can kind of say, what's the opportunity for improvement? And so here's a bunch of different types of developments in a particular place. And basically what it says, if the perfect well time, if the technical limit is 2, so we could do 2, people have done 2 is possible. How much could we improve these different kinds of wells? And this would be the maximum improvement from that limit. So here's an example where, hey, here's a pretty shallow deal, and you know what? These wells, we could probably improve the time by 76%, So, but by the way, here's one, not a lot of improvement left. If well cost is driven by time, if 33% of the well cost is time related, this is the possible cost reductions. If 50% of the time is well cost is time related, and of course this all depends upon rig rate and cost of casing and mud and so forth. You might be able to save 20 to 35% of well costs. And so this can say, where should I put my improvement efforts? Well, I think I'll start where these numbers are big because there's more slop. It's going to be harder to improve that because it's just closer to being better. So that's an example of that. Here's an example where you can compare not just the average for these things, but these benchmark wells have kind of averages in here. These are what happened to technical limit. Interestingly, the best composite time for these series of wells right here was actually here. So they've actually performed this. They have the best composite time for all these wells is 2.5, so it is possible. It's just not occurring. So where's the one that has the most opportunity improvement? Well, it looks to me like these deviated ones, this well type 2 deviated ones, are kind of the farthest away from this. If you deep set casing, well, it improves things a little bit. Anyway, this is a way to begin to think about how far am I from good and having questions about what I could do to improve. Here's another example of some, this was in 2008, and these were shale wells, unconventional shale wells people were drilling, and you say, let's just calculate the perfect well time for these things, and it varied from 2.9 to 5.5 on different types. And interestingly, you come in here and here's a well, you know, it has a perfect well ratio of 5, and you're going, and they say, we're drilling these wells in 14 days. Isn't that great? And I go, yeah, that seems pretty good, but you know, perfect would be 2.5. So that's a 5.3, 5.4. It seems like you could do better than that. Well, you know what? When you tell somebody that, it's like, I don't know. That sure doesn't seem like it's possible to me. But it's like, you know, 3.5 times the perfect well would be a 9-day well. You know what? They're drilling those wells in 8-9 days now. In other words, they did it. And so these wells often have perfect well ratios less than 3 now. And in 2008, it kind of seems fantastic. Can that really happen? Well, it did happen. And so, in other words, what do you benchmark yourself against? And there's one thing I know about improvement, and there's only actually one rule with improvement, and that is if you do not think it will happen, it will not happen. Because you are not, you're not going to, if you try it, it doesn't mean you'll get it. There might be reasons for hole stability or, you know, fractured formations or something that would keep you from doing this. But if you don't try, it's not going to happen. And so here's an example of, you know, use this to kind of bound well cost estimates. It's one last thing, and we'll start asking questions and try to answer questions in a couple of minutes. What happened is, look at 23 exploration wells. I think these are Gulf of Mexico. I'm not sure what they were, but these are the perfect well ratio and the cumulative probability distribution. So 90% of the wells had a perfect well ratio less than 13. 10% of the wells had a perfect well ratio less than 4. Look, here's one that actually had a perfect well ratio of 2.2. But here's one that had a perfect well ratio of 22. That's a bad one. That's a problem, isn't it? Well, the average perfect well ratio was 7.6. The P50 was like 6.5. And because the bad wells are bad and the good wells, you can't have a well drilled 0 days. And so the average is always going to be higher than the mean. But so here's what we did. Compare this with 7 exploration wells from a different company. And you know what? They actually overlaid. It was crazy. I thought this was crazy. And so it was like, this is ridiculous. And it kind of is ridiculous. But basically what it said was, and this distribution kind of seems to be what happens a lot in exploration wells. In other words, the process gives you this kind of distribution based on the loss and waste due to decision and uncertainty in this. But the mean was 8.5, and the actual, 50% was 6.1, very similar kind of deals. And so here's the interesting thing about this in terms of bounding well cost estimates. And this actually happened. Would you AFE an exploration well with a perfect well ratio of 4? So in other words, you're going to create a well cost estimate for a well. You're going to create an estimate for how much it's going to cost to drill. And you go, I think we can, that's the kind of time estimate we should have for our exploration well. And you know what? That might be a good target. In fact, probably is a good target. On a well trying to get a perfect well ratio of 4, it's probably a good idea. And it's probably laudable to attempt to do. But I wouldn't tell my boss I was going to do it for that, and get him to say, okay, this is how much money we're going to allocate for the exploration well. You know what? Because probably it won't happen. And so it's like, I'm not a very good golfer, whatever. What should I try to get on this hole? Well, I think I'm going to try to get a birdie. But I shouldn't bet my buddy. I'll tell you what, I'll bet you $50 I get a birdie. It's like, well, you're probably not going to do it. And so that's the idea of using this to kind of understand what the cost distribution in a program. And so the 90-second answer, we'll start answering questions to this, is, this is the fastest it can possibly be done, and it can tell us how much and if we have improvements. And this little spreadsheet, which we're going to send you a link to this, post this webinar survey this afternoon. If you have any questions, email me, fbrett@petroskills.com. I'll try to answer them. And put in the subject perfect well, so I make sure I know what it is. Something like that. And it's better, or it compares with the technical limit and the days per 10,000 feet because it's quantitative. It kind of normalizes differences and it's non-arguable. That's the quantitative thing. And it's easy to do. And you can use this to kind of understand what improvement is possible and start creating a conversation about, what can we do and how efficient are we and what can we do to improve instead of arguing about how good should we be. And so understanding the causes of inefficiency and then trying to figure out what to do about them. So anyway, happy to try to answer questions now. I guess we got 12 minutes or so left. So Clay, you got any questions?
Yeah, we've got a few questions that have come in, and again, feel free to type any questions that you have into the chat, and I will add them to the list here. The first question is the perfect well ratio valid for all geographies?
Good question. Is the perfect well ratio valid for all geographies? And I guess we can say rocks. These are rocks in North America, South America, Asia, Europe, and so it has been used, all over the world. And so I guess the answer to the question is I think it is. If you got sonic logs, let me say this: it's valid if drill bits cut rock the same way around the world. I'll tell you what does cause perfect well changes, though, is the capability of rig crews will change operational skill-based loss or waste. And so, a really well-trained rig crew on a deep water well, maybe they can operate more efficiently than a rig that you just picked up, well, probably can, with an inefficient crew. So what is physically possible, I think, is the same. What you can practically achieve, will probably depend upon the specific situation, and so a perfect well ratio of 4 might be pretty good, but in one place, based on what is practically possible with equipment and so forth, as compared to a perfect well ratio, maybe 2.2 is what people should target in other areas. So hope that answers the question.
All right. Next question here is, what effect, if any, do advances in drilling automation have on technical limit and the perfect well ratio?
Okay. What they should do is, if drilling automation functions properly, which you can, you can, autopilots on airplanes and robots in Amazon stores or Amazon warehouses. What it should do is it should make achievement of the perfect well or technical limit more likely and reduce the variation. You see, for example, just pick this area here. Here's wells in the Middle East. The average perfect well ratio in that operation was what, 5? Well, could have done it in 3.8. The worst well was 6. Well, the reason you had 6 is something went wrong, losses or decisions or something. The reasons you had 3.8 is because you did it better. And so the thing about that would be automation would I would think tend to narrow this band and push it down. So that's what I think would happen, and that's good.
All right. Then there were a few questions that came in regarding slide 28, and they basically centered around your example of unconventional wells. Do you have some examples of improvements made to bring the perfect well ratio from 5 to 3? And then somewhat related was, are there any indicators in the perfect well spreadsheet that would point out areas for improvement?
Okay, we have the perfect well spreadsheet will tell you, the perfect well time per interval. So you can say for each one of these casings hole intervals, how long is it going to take? And so the area with the biggest gap has the biggest biggest possible improvement. Let me tell you something about improvements in general. This slide right here, dang it, shows that what happens and says what are the key improvements that cause that to happen. And man, look at that, that's crazy. Okay, this is very interesting and is similar. There is not one thing that people need to do that make big improvements that happen. Look at improvements that step changes that people have in improvements in drilling operations, and I've done this with dozens of different types of operations. And you say, what was the difference between the old way and the new way? It is almost always many things, and the things, or one or two, two or three things that make big changes don't account for most of the changes. The one exception to that is air drilling. If you can get air drilling to work in a hard rock area, you can make a big change. A big change. And by the way, this perfect well time is accounted for with mud, not air. So, the only way, and so my point is, drilling operations, there are very, very few $100 bills laying on the ground that you can pick up, but there's billions of quarters. And it's about picking up quarters, not about, finding the $100 bill. And so it's lots of improvements in many, many, many different things. And interestingly, the better rigs get as far as drilling goes, we got PVC bits, it's working great, 1 bit per hole section, et cetera, the more a rig ceases to be a drilling rig and becomes a tripping rig, because running pipe becomes a greater percentage of the total time. And of course, that's all about, making connections properly, those kinds of things. And so when you say what caused the improvement, on slide 28, it's not like, oh, there's one thing that did it. It's like there's a lot of things that did it. And I guess let me say this. That's, what that means? That means drilling engineers are valuable. The reason it is, it's not like I'll email you the one thing that'll improve everything. It's like you guys had better get to work and understand all the details, because it's improving these many, many things, not these one things.
All right, and then there were a few different versions of this question, so I'll paraphrase how does the perfect well method, is it more or less predictive for exploration wells versus development wells, and the same thing for horizontal versus vertical?
Okay, what happens is, as you get to more controlled development, the difference, the variation, the percentage variation in well performance goes down and gets lower, and that basically means you're getting more predictive and more the process is more under control. You have less loss, and your losses are smaller. And so in exploration wells, there's a wider variation of perfect well ratios. If we showed this, for example, in this thing right here, you have an exploration well, dang it, we can have a disaster well at a perfect well ratio of 20, actually perfect ratio of 37, I've seen. Or you can have, everything goes well, you can get a 3 or 4, that's conceivable, it is possible. Happen to understand the situation. And so exploration wells have a greater variation in perfect well ratio. As you start understanding and reducing loss and reducing waste, as you improve performance, you start getting a tighter distribution of well types. And I have another example to show kind of a particular well types. And so in a development well, you might have this curve will kind of go from maybe start out there at 2 to 2.3, dang it. Got to go backwards here, sorry. And then kind of come up here, and maybe the average is 3, and then kind of there's some wells that might be 6, or that would kind of be a bad well. And so the distribution kind of goes like that. So, and it's morphing from, you know, we go, if we're going to drill, we do an exploration well in Greenland and do an exploration program in Greenland, you'd probably have some distribution like this. We do a development program in Greenland, it's going to start moving to the left.
All right. And then this is the last question we've received so far. So this is last call, so to speak, on if you want to get your questions in. Otherwise, this will be the last one. How much better is foot-by-foot rock strength versus by-hole selection?
By whole section. By whole
section, sorry.
Okay, what happens is the spreadsheet you're going to get, you can plug a sonic log in there, and it will calculate the rock strength in that unconfined compressive strength based on the sonic log, for hole intervals. And so what this spreadsheet then does is say, hey, plug in the average or kind of the rock strength for that whole interval, and if someone were to jimmy the spreadsheet or make it so that you actually calculated the rock strength and penetration rate foot by foot, it would be better and more accurate. The only thing it makes a big difference in is if there's like a way big difference in rock strength in a particular hole interval. And rock strength kind of varies with the age of the rock. So Cretaceous rocks is a lot harder than Miocene. It's had more time to cement and so forth. But and so if you had a casing interval that went from across the Cretaceous boundary with softer rocks above and harder rocks below, you might the bottom of the hole might be way harder than the top, and so it would be more accurate. So there is an improvement or opportunity for improvement there. Okay, other questions? There's one other question maybe just came in.
Yeah, so what should be the optimum PWR for ultra deep water, high pressure, high temperature wells?
I would put, okay, the question is this an exploration? I would put it something in this kind of profile, and something, if you could do a 6 to, this kind of thing in here would probably be okay. It would not be a bad performance to start out with. And so this is kind of the idea of what is possible and where should you realistically start. And so, the first high pressure deep water well you're going to drill is going to be bad, or not so bad, more likely to be inaccurate because you won't know what to do. Some of these, have perfect well ratios of 4 or 5. So I'd say kind of an optimum would be, if you could actually achieve this is practically optimum. I mean, let's say optimum is achievable and is very good performance. And so, it's like playing golf, what should you do? Well, a birdie's good, man. An eagle's really good. What should you plan on? Well, I don't plan on those because, if I get them, it's luck, really. So, and depending upon your area, just start doing it and seeing what's right, trying to get benchmarks from other operators and so forth. So,
all right. Well, that wraps up all the questions we've got. Thank you, Ford, very much.
Thank you, guys, everyone.
Thank you, everybody, for all the questions and for spending your time with us this morning, this afternoon, this evening. Again, we will send all this information out along with a link to the spreadsheet. And then just my marketing plug, go to the Tech Tuesdays link on the petroskills.com homepage. We'll be adding a few more over the next couple of days, and check out what we've got over the upcoming weeks. And we hope to see you again. Stay safe, everyone, and thanks a lot for joining us.
Thanks.